Today I'm going to explain why grounding equipment makes us safe. And in the process, I'm going to explain why it should make it more dangerous, but doesn't. Before I do that, I'm going to explain a little bit of the basics. I'm going to talk about something called Thevenin's theorem. Thevenin's theorem tells us that any circuit, I'm just going to draw something here. I have a battery, and I'll just draw some resistors here to represent some circuitry. Here, let's make it kind of complicated here. I'm just going to stick to DC, no AC components, no active components here. And I'll just put some numbers here. 10 volts, 10 ohms, 10 ohms, 20 ohms. I'm just making these up as I go along. 40 ohms. These represent the components of a circuit. And let's say that this circuit has an output right here. And Thevenin's theorem says that any circuit that produces an output, in other words, we have a voltage source and it gives us something useful on the end, whether it's just a voltage to power something, or if it's a signal that we use, such as an audio or video or radio or whatever, that this circuit, no matter how complex, can be represented by a single voltage source and a single resistor in series. So I'm going to erase all of this and put a resistor right here in series with that. And of course, this voltage would be different. We can calculate that out. In fact, if you want to learn more about Thevenin's theorem, I'll just put 5 volts here because I can. If you want to learn more about Thevenin's theorem, you can read about it in the lessons at RSD Academy. I have linked below. And I also have a video about that. You can also, that is embedded in the lesson. And it explains just some basics and shows how we can take a complex circuit and do some simple calculations such as series and parallel resistors, Ohm's law, and whatever, and eventually determine that this circuit acts like it has a single voltage source and a single resistor in series. If we want to determine what that is, it's a fairly simple process. What we do is we find the open circuit voltage. So we put a voltmeter across the side with no load on the circuit. Now there may be components in there that are carrying current that are parallel to this, but we don't care about that. We just want to see what the voltage is when we put a voltmeter across the output. And we take that voltage, and that tells us what the voltage of the battery is, because in an open circuit we have no current. If there's no current flowing through this resistor, that means there can be no voltage drop across it. So if we put a voltmeter, let's put the black lead here and the red lead up here, I'll just put a mark there, and we measure that voltage. Whatever voltage is here is the same voltage as here. So we have no voltage drop. So the open circuit voltage tells us the voltage of that voltage source over here. Now, the real voltage might be something completely different, but this is showing us what it's going to act like. Then what we do is exchange our voltmeter for a current meter. And of course, a current meter acts like a short circuit. A voltmeter acts like an open circuit. A current meter acts like a short circuit, so we are shorting this together and it gives us our short circuit current. And let's say we got 1 amp there. Well, that means that we're having 1 amp go through that resistance. And of course, since the current meter is a short circuit, it can't develop any voltage. And so there's 0 voltage here, and whatever voltage is left over in the series resistance is the voltage of the battery. Remember that Kirchhoff's voltage law says that all of our voltages in series must add up to our source voltage. Well, there's only 1 voltage, so that's going to be 5 volts across there. So we're losing 5 volts now. So we start with 5, we now have 0, so we lose 5 and 1 amp. So 5 volts and 1 amp, that's going to tell us that that is a 5 ohm resistor. So we just determined that by the open circuit voltage and closed circuit current, but I show in the lesson how you can calculate that out if you have some series and parallel circuits, just to show that it really will act that way. So that's Thevenin's theorem. Once again, any circuit that produces a usable output that has a voltage source and gives us some voltage on the outside can be represented by a single voltage source and a resistor in series. And that doesn't matter what kind of circuit it is. It can be an audio circuit, a radio circuit, or including the power grid that powers our houses acts like a Thevenin equivalent circuit. Now, when we have just a battery, this resistance is called the internal resistance. So we can take a battery, check the open circuit voltage, the short circuit current. That's going to tell us what the equivalent voltage is inside and what the series resistance is, once again called the internal resistance. But other circuits, we call that the output impedance. Even if it's purely resistive, it might have inductive and capacitive components, but no matter what it has, we call that the output impedance. So every circuit has that, including the power grid. So the power grid has generators out there. I'll represent that with the AC source. That goes through transformers, gets transformed up to higher voltages, back down to lower voltages, other transformers, moving it here, moving it there, and finally we eventually get down to here in America where we have 120 volts as our standard. If we take the open circuit voltage, which we'll probably see 120 volts, so there's our voltmeter. And so that's our open circuit voltage. Then if we short it out, we don't want to do that. We would have to calculate that by putting a load on there and putting some loads and seeing how it acts with a load on there. So we'd put some kind of resistance here and measure how much voltage drop we have, and then we can use Ohm's law and Kirchhoff's voltage law to figure out what the other resistor is. But you can look at the Find the Mystery Resistor exercises in the lessons to see how that could be determined. But the end result is that this whole power grid acts like a generator of some sort with a series impedance. Now, of course, that's going to have capacitance and inductance as well as resistance, but we can represent that for this purpose as just a resistor. So we need to know that to understand why the grounding of circuits protects us. So now let's take a look at the system, and I'm going to explain why grounding it should be actually dangerous. So let's take a look at our system real quick. Here is our generator. Once again, we go out to some transformers. I'm just going to draw this real quick because I will be erasing it. And eventually we get down to our 120 volts. So that acts like a 120 volt generator with a resistor in series. So let's just draw that. And there it is, 120 volts. And what is this? We'll worry about that later. So why is this dangerous? Well, it's not yet because it's not grounded. I'm going to put my little green man here. And if our little green man is wearing good rubber boots and it's a good dry day and he's well insulated, he's going to be pretty well protected no matter what's going on here. But we don't assume that. We always assume that our little green man, meaning you or me, is grounded. We always assume that we're barefoot on a wet concrete floor that has good connection with the earth, so we are grounded to a true earth ground. We just assume that because that's a worst case scenario, and that's why electricity can be dangerous if the system is grounded. It's not dangerous yet because, well, just like if you take a battery, I'll just draw a battery here. And let's say we take a voltmeter. I'll represent my voltmeter with my black and red pins here. And if I take the red lead and I stick it here, what's it going to tell me? Let's say it's a 100 volt battery. How about 120 volts? So I stick my red lead here. What am I going to read? Well, if my black lead's just hanging in the air, I'm not going to read anything. I'll see 0 volts. Does it mean there's no voltage there? No, it just means I'm not getting a comparison between this voltage and another. Remember that any voltage is meaningless unless I compare it to another voltage. And we can't get anything useful unless we create a loop for current to flow. Well, I'm not creating a loop for current to flow or even to make a measurement, so I get nothing. If I take the black lead, put it here or anywhere, same thing. If my red lead is just floating, I don't get anything. So without having a connection to the top or to the positive side and to the negative side, I don't have any current that can flow. So if I have a little green man here and he touches that side, well, he's not connected to that side, no problem. If he touches this side, he's not connected to that side, no problem. Only if he touches both sides. Now he has 120 volts across him, and if it's a wet day, wet skin, good current connection to this side, he could get enough current through him to be deadly. Remember, they say that it's the current that kills, not the voltage, but you can't get the current without the voltage. So here we have enough voltage to push enough current through to be deadly, but only if I'm touching both the positive and the negative of the battery. And the same thing goes for this. So if this is just floating, not connected to ground, it doesn't matter whether I'm connected to ground or not. If I touch this side, nothing's going to happen. If I touch that side, nothing's going to happen. Only if I manage to touch both sides would I be in danger. So keeping this floating would actually keep us safe, even if we're connected to ground. So it's actually dangerous to connect our power equipment to ground. So why do we do it? Well, because those wires are going all sorts of places. They're going on power poles, they're going underground. Underground, maybe some water might flood in there and we get a short and get a connection to ground. And which side's going to connect to ground? I don't know. Could be either side. I don't know which side it is. Or maybe something else causes it to connect to ground, or maybe if it's over land, something might blow a pole down and then we get a connection to ground. Might fall on a fence that's well grounded. And so now we have a connection to ground, and now I'm connected to ground. This is like a short circuit here. I'm connected to this side of the circuit. And it doesn't matter which side it is. Could be the other side connected to ground. Either way, now if I touch this end, I'm in danger. That end I'm pretty safe, but this end I'm in a lot of danger. And even this end, who knows what might happen. It still could be unsafe. So the reason we ground equipment is if we ground it ourselves, number one, we know it's grounded, and so we can deal with it. And we know which side is grounded. So we don't know, if it's not grounded, we don't know which side is dangerous if we get a short to ground, if we get a fault to ground. Well, it could be this side, could be that side. So which side is dangerous? We don't know. So we ground one side. Now we know that this side is the safe side because it's grounded. Maybe that'll make a little sense in a couple of minutes. So now, if I'm grounded, and that's grounded, if I touch this, I'm probably pretty safe. There could be, some miswiring where it's wired backwards, or if there's a lot of current flowing through there, that could raise the voltage, maybe to a dangerous level. But theoretically, compared to me, remember voltage is always a comparison between one voltage and another. Well, the voltage here will be the same as the voltage there. So if I put a voltmeter across there, I'm going to read 0 volts because there's no difference. Remember, if you put your red lead at the same place as your black lead, there's no difference between the voltages. So I read 0 volts. Only if I have two different voltages does the voltmeter tell me what the voltage is. The voltmeter tells you the difference between two voltages, just like any kind of a pressure measurement. So my danger is, of course, what happens if I touch that side now. That's why this is actually dangerous, because now that's grounded, I'm grounded, I touch that side, I could be electrocuted. So what we do is we protect the equipment. I'll represent our circuit with a resistor here. That just represents whatever our load is. Could be a motor, could be any kind of electronics. And we could double insulate it by putting a plastic case around it and make sure that there's no way that we can touch anything. Or sometimes we need, for whatever reason, to put it in a metal case. And so what we're going to do is make sure that these wires are both insulated. I'll just show that as these little lines here. So these wires coming through are insulated from the case. And so now, if my little green man touches that case, I'm still safe, even though I might be grounded. Put my little connection to ground here through my wet concrete and bare feet. And if I happen to touch the case, well, it's insulated, so I am safe. But what if something happens to the insulation? What if the insulation breaks down and we get a connection? What if something happens inside? In fact, sometimes solder can actually grow little tiny, what they call tin whiskers. Little needles of solder will grow, and it could go and make a short. There's all kinds of things that could go wrong, and somehow this could connect to the case. Most likely it's probably where the insulation could break down there. Now what's happened? Now this voltage here is connected to the case. I'm touching the case. I'm going to ground. This side is going to ground, so I have my circuit that comes through here to ground, and now I'm in danger. So we still don't see, why did they ground it? It looks like it makes it more dangerous. Well, here's how we make it safe. What we're going to do now is we're going to ground this case. Now, what does that do? Let's take me out of the picture for just a second and take out the short for just a second. Now, if we get a short on this side, we should be safe, but there could be faults that even that might not be safe. But let's just assume we're only worried about this side. This side, if I'm grounded, the voltage is the same, so I don't have any impetus to push current through me. Only where I get a different voltage, 120 volts difference, might I be in danger. Now what happens if we get a short right there? Well, now we have a path to ground through the case. Now what most people will say is that this will conduct the electricity to the ground, and therefore the electricity can't go through me. Well, it's just a little more complicated than that, and probably a little more interesting. So I'm going to explain the real reason, because it's a myth that electricity always takes the shortest path to ground. The electricity is not going to go through the case because it's the shortest path. Electricity takes whatever path it can. So why, if we know, well, it's going to take a path through the case to ground, but if I'm touching that case, I'm still creating a path to ground, so some of that electricity should go through me, and it will. So the question is, how much, and how does this make me safe? Well, let's go and take a look at what the equivalent circuit is. So we have this internal impedance, which is part of the system. We have our resistance, which is our load. This is our motor, or whatever we're using to consume the electricity. And I'm also like a resistor because I'm a path to ground. I have a certain amount of resistance. So I can represent myself as a resistor going to ground. So that's me, connected to ground. And this case has a very small resistance, but resistance it has, so that case can also be represented as a resistor going to ground. So what we end up with is three resistors in parallel. So let's just draw what that is there. So here is our load. Here is our case. And here is me. And me is connected to ground. The case is connected to ground. But there's no connection here so far. Now let's put some resistors here so we can come up with some numbers. Let's say this is 0.01 ohm. That's probably a little bit of a high resistance, probably be less than that, but that's a number we can work with. And let's say our load right here is going to be, let's say 100 ohms. And just to make the numbers easy to play with, let's make that 100 volts. So 100 ohms, this doesn't really affect anything right now, except if we look at this, we see there's 100 ohms, 0.01 ohms. How much voltage am I getting across my load now? Well, knowing Kirchhoff's voltage law, we know that the voltage here and the voltage here must add up to that voltage, and the voltage will be distributed proportionally. So the bigger resistor gets the bigger voltage. So this has about 1,000 times more voltage than that. So this is going to be basically 99.9 volts here. And then 0.01 volts here, a very small amount of voltage there. So we lose very little voltage, have almost all of our voltage across our load, and so that's working normally. Now let's see what happens if our case touches the hot wire there, the one with the voltage, the one that's dangerous. By the way, we call this wire the hot wire, the one that actually is dangerous. Over here we call this the neutral wire, because it's connected to ground. We don't call it ground because we can have big currents flowing through there, and because this does have resistance, whenever you have current going through resistance, you will get a backup of voltage. So if we go to where the current is going in, we get higher and higher voltages on that side where it's going in compared to where it comes out. And so if we have, even with this tiny little bit of resistance, if we have big currents, we can get some voltage here. So they don't call that the ground, it's the neutral, it's the return wire, and the ground should have no current flowing through it. Only if there's a fault would we expect anything flowing through the ground. In fact, it would only flow through this ground and then through the earth back to this one. So That's why we call those the hot and the neutral. The neutral is connected to ground somewhere, but not near your appliance. So let's get this clutter out of here. So we get that short over to the hot wire. Now let's assume this case has a resistance of 0.001 ohms, very, very low resistance. So what's going to happen? Well, first of all, let's look at the total resistance here. We have two resistors in parallel, and we know that when you have two resistors in parallel, the total resistance will be less than your lowest resistor. So our total resistance of these two together is going to be less than 0.001 ohms. In fact, this is so much smaller than that, this doesn't even enter into the game. So basically now we have 0.01 ohms with 0.001 ohms in series. Let's just get this out of here because it doesn't even factor in anymore. It's so much bigger. So there we have our full circuit, our generator, the output impedance of the system, our case, which is 0.01 ohms, going to ground and returning to ground back there. So we do have a full circuit. So we do have current flowing. So how much current are we going to have flowing? 100 volts and 0.011 ohms. It's going to be a heck of a lot of current. It's going to quickly blow the circuit breaker, but it could kill you before the circuit breaker goes. So we need to protect us from this voltage. So how much is it going to be? Well, this is 1/10 of that. So the voltage here is going to be 1/10 of the voltage there. And we have 100 volts to deal with. Remember, Kirchhoff's voltage law says that this voltage plus that voltage must add up to this voltage, and the voltage is distributed proportionally. So we're going to get 10 times more voltage here than we do here. So 100 volts, we're going to get basically 90 volts here and 10 volts over here. Now in reality, this is going to be a lower resistance because that case has a very low resistance, assuming we have good electrical connections. But even if we don't, if we have even as high as 0.001 ohms or 1 milliohm, we are going to get only 10 volts across here, and 10 volts is not enough to push a dangerous amount of current through a human body, even under the worst case scenario. This is like a well cleaned out drain. The electricity goes down the drain so fast it can't back up enough to be dangerous. Where if this was a high resistance, it would be like a slow drain, and the electricity could back up behind the resistance to a level that could be dangerous. But this drain scoots right out, can't back up any, so I don't get enough voltage to be dangerous. So they say that it's current that kills, not voltage. Well, it takes the voltage to push the current. So the myth is that the reason, let me just draw these as resistors again. Oops, that goes to earth ground. What they say is that since this is 100 ohms and this is 0.01 ohms, actually that's 0.001 ohms, this is the lower resistance. And of course, if I put myself here, and of course I'm grounded too, and if I manage to touch up there, let's say a worst case scenario is I'm about 500 ohms. So the myth is that the reason this protects us is because this resistor is the shortest path to ground, so the electricity goes through that resistor instead of going through there or going through me. Well, that's not true. Electricity will take whatever path it can. Some of it's going to go this way, most of it's going to go that way, but some will go that way. So what keeps me safe? Well, this resistance is so low that even though the lion's share of my current is going through there, it can't back up enough voltage behind it. It's just a good clean drain. The voltage doesn't back up, so I don't get enough voltage here to be dangerous with my worst case scenario of being around 500 ohms on a wet day with my foot on wet concrete with a bare foot. So, and a lot of sweat. And that is why grounding protects us. So actually, grounding should make it more dangerous. But what we do by grounding our equipment is we control where the grounds are so that if there is a ground fault, we have them in the right place, that we can keep ourselves safe by making sure that when something goes bad, that the path to ground has such low resistance that we cannot build up a dangerous voltage. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.